Hello friends, last class I discussed about the development of the organic light emitting diode, history of the organic light emitting diode. So before organic light emitting diode, what are the devices were used for the display system? Okay, today, so after those devices, after development of those devices, an organic light emitting diode that was discovered. Okay, so why it is important, that I have already told on the last few lectures. So organic devices, why it is so much importance. Okay, now today I will tell about the when the first organic light emitting diode is was discovered. Okay, so after that I will tell about the basic structure of the organic light emitting diode. Okay, so organic light emitting diode. Alright, organic light emitting diode, the short form is the OLED. Okay, so the organic light emitting diode that is totally driven by the electroluminescence effect. Okay, so electroluminescence effect. So first I will tell when the electroluminescence effect is was discovered. Okay, so it is a one kind of the electroluminescence. What is the electroluminescence effect? That I told in any device. Okay, so if we apply some bias, okay, the electron and hole will inject inside the device, and this electron and hole, these are recombined with the each other. Okay, then we will get a luminescence effect. Okay, light. So this first electroluminescence effect was discovered inside the organic material. Okay, in the year of 1953. The organic material is the acridine. Okay, in this organic material, first electroluminescence effect that was discovered in the year of 1953. So after 1953, in the year of 1963, atrazine is the one of the popular organic semiconductor. Okay, so inside the atrazine, the electroluminescence effect that was discovered in the year of 1963. Okay, these are the small molecules. Okay, so organic semiconductor, this is divided into two parts. One is a small molecule and another is a polymer. Polymer means that consists of multiple hydrogen and carbon bonds. Okay, so after that, in the year of 1983, electroluminescence effect. Okay, electroluminescence effect that was discovered inside the polymer OS. Okay, in the year of 1983. So electroluminescence first, this electroluminescence effect was discovered in acridine and atrazine, such kind of the small molecule materials. After that, the year of 1983, the same effect that was found in the polymer OS. Okay, after that means what I told, that the OLED that is driven by electroluminescence effect. Okay. After that, in the year of 1987, okay, 1987, first small molecule based OLED was implemented. Okay, in the year of 1987. Okay. After that, 1990, polymer OLED was implemented. So both small molecule and polymer OLED both can show high electroluminescence efficiency. Okay, so the performance of both the OLED are very good. Okay, after that 1990, that is the 1987 small molecule, 1990 polymer based OLED, these are implemented. Okay, so in the year of 1997, okay, year of 1997, first OLED was commercialized. Commercialized means this OLED. So in the year of 1997, okay, such kind of the OLED were discovered which can used in the different lighting and application and display application. Okay. right? So this is commercial inorganic OLED. So in our daily life we can see so many inorganic light emitting diode. Okay, and so for lighting application and display application, so you can see the small inorganic LED that can use for lighting purpose. Okay, so similarly 1997, in the year of 1997, the OLED was commercialized for lighting and display application. Okay, after that, the year of 2000. Okay, flexible OLED that was commercialized. Okay, the flexible OLED for display application. Where you can use the flexible OLED normally, we can use the flexible OLED in high resolution TV screen, high resolution TV screen, and smartwatch and so on. Okay, so what is the difference between this OLED and the flexible OLED? Okay, so OLED we can design OLED. Okay, if you want to design any device, we need one base or substrate. Okay, right? The base of the any device, that is the substrate, that is called as a substrate. Okay, normally the OLED and flexible OLED. What are the difference between this OLED and the flexible OLED? Right, so OLED, so if we deposit, if we fabricate, if we design any kind of the OLED on a substrate like a glass, okay, like glass, so that is a normal OLED. Okay, right? So if we design such kind of the OLED on the flexible substrate, flexible like a bending substrate. Okay, plastic you can bend plastic, right? So plastic, cloths, papers. Okay, these are called the flexible substrate. Okay, right? So if you see the flexible OLED, that will be like that. Okay, what is the difference between flexible? Suppose, so one of the main application of the OLED is the display system like TV. Okay, flexible OLED. If we see flexible OLED TV, so it will be like that. Okay, flexible TV. It is like bending. Okay, bending. You can see the bending kind of the display. Normal OLED, nothing is there. Normal display system, but it has advantages over the inorganic LED. Okay, right? So flexible OLED, so for that normally plastic, paper and cloths, these are used as a substrate, and here glass, over the glass ITO layer is there. Okay, ITO glass, this is used for normal OLED. Okay, so both can give high efficient, right? So nowadays this is more important. Flexible OLED is more important as compared to the normal OLED. Now I want to discuss about the basic structure of the OLED. Basic structure of the OLED. Based on the structure, OLED can be divided into three parts. Okay, single layer, double layer, and multi-layer. Okay, single layer, double layer, and multi-layers. These three kinds you can divide. Okay, right? So single layer means, so if you want to design it, it's like a diode. Okay, if you want to design any kind of the diode device, getting light emitting diode, one is the anode and cathode. These two electrodes are mainly required. Inside the anode and cathode, in between anode and cathode, you can insert multiple layers. Right? So for single layer, so this is anode and this is cathode. For single layer, only one organic semiconductor layer is there, that is the active layer. Okay, so it can be actually the electron and hole will be injected inside this organic semiconductor layer, and that will emit light. Okay, in case of the single layer, right? The cathode will transfer electron and hole will transfer, anode will transfer hole. Okay, and both will be recombined inside the organic semiconductor layer. That is also known as emission layer or emissive layer. Okay, because here I am getting this layer, I am getting the light, right? Now is the double layer. In case of the double layer, you see cathode, I am representing cathode and anode. Okay, and one is the conducting layer, emission layer. Okay, in this case what will happen? The electron will transfer from cathode to this emission layer, and hole will transfer from anode to conductive layer and pass to the emissive layer. Okay, inside this emissive layer, the electron hole both are recombined and produce light. Okay, only one conducting layer is there and another is the emission layer. That will be p type and this will be on like an n type. Okay, this is the p type, the hole will transport through p type conducting layer. This n type, the electron will transport and it will remain inside the emission layer, and this conducting layer, that inside this emission layer, electron and hole both will recombine. Okay, next is the multilayer. Okay, in this multilayer, I am drawing the structure. So multiple layers are there: cathode, anode, electron injection layer, electron injection layer, electron transport layer. So injection layer and transport layer. So instead of injection layer, we can only use the transport layer. So in some devices, only single layer is used. In some devices, both layers are used. Say injection layer and the transport layer. Okay, middle one is the emission layer. Emission layer, the whole transport layer and whole inject layer. So by name you can think about that whole inject layer. It is one kind of the layer which can inject hole from the cathode and transfer to the whole transport layer. So the whole transport layer helps hole to transport from injection layer to emission layer. Here we will get hole. In this way, the electron will be injected by the electron injection layer, and that will transport through the electron transport layer inside the emission layer. In this layer, we will get the light. Okay, now what kind of the light we will get, that is depending on the emission layer, the molecules of the emission layer and band gap of the emission layer. And moreover, so if you want to get a efficiency, if you want to calculate the light coupling efficiency, electron emission efficiency, everything is depending on the emission layer. Okay, so if something happen in the other layer, so you will not get proper efficiency. Okay, it will help how the, because the hole will transport inside the emission layer and electron will transport inside the emission layer. In this emission layer, so suppose 100 number of electron hole pairs are gathering at the emission layer. Okay, so you should get the 100 amount of efficiency from the emission layer. So how it is emitting from this layer? Okay, that means light coupling efficiency, electron efficiency, that these are totally depending on the emission layer. And what kind of the light you will get, that is decided by the band gap of the and molecules of the emission layer. Right? Now, suppose here I told that instead of injection layer, you can only use the electron transport layer. If you use the multiple layer, you will get the high efficiency. Suppose I want to discuss about the each and every layer. So I am not discussing injection layer. I want to discuss only the electron transport layer and the whole transport layer. Okay. First, this is anode. Okay. This anode I can use as a indium tin oxide. Indium tin oxide, that is a transparent conducting anode which can be transparent, because the emission layer, right? So you will not get the light from the emission layer. This will produce the exciton, but the exciton will be illuminated through this ITO layer. Okay, through this ITO layer, because this is a vertical structure. Okay, this is a vertical structure. This will produce light, but that will be propagate through the whole transport layer and through the light. So if you see the display, the upper layer, this layer should contain indium tin oxide. So indium tin oxide, this is the high work function. Okay, this is the high work function. This should be high work function. So what will happen? Indium tin oxide, that will so whole transport layer. So whole transport layer. So electron layer, the anode, that will transfer whole to the whole transport layer. Why the work function should be high? To get efficient whole transport, the work function of the ITO should be high, right? So that will give the hole inside the device. So anode will give hole into the device. Next is the cathode. Cathode should be like aluminum or silver. Okay, so aluminum is one of the important. So this should be low work function. The anode should be high work function, and cathode should be low work function for getting electron. Okay, from the cathode to the device. So this should be low work function, and this is the high reflective index. High reflective index. Okay, no electron will be propagate outside of the device. Okay, this should be fed into the device. Okay, so this is the aluminum. You have to, if you use the aluminum, this is the low work function, and this for efficient electron transport we have to use the low work function material. Okay, metal as a cathode. Okay, that will give electron to the device. Now come to the whole transport layer. So what is the function of the whole transport layer? So the by name whole transport layer. So it is a transport layer which transports whole to the device. Okay. So what is the function of this? So this transport whole through the device. Okay, and it will restrict electron from the outside of the device. The band gap and the energy level diagram should be such a way it can only transport the whole from the anode, and it will restrict electron from the opposite or side of the device, right? So electron cannot penetrate. Okay, electron cannot penetrate inside the electron transport layer. Okay, the most popular whole transport layer is the P dot PSS. This is one kind of the polymer layer, conducting layer, polymer conducting layer, P dot PSS. Right? After that, I will tell about the electron transport layer. So opposite function of the whole transport layer. It transports electron through the device. Okay, it transports electron. It injects the electron from the cathode and transport the electron through the device. Okay, it will collected by the emission layer. Okay, and same thing. So it restricts hole from the opposite side. It restricts hole from the opposite side. Most popular electron transport layer is the BCP, or you can also use AlQ3. So these are all are the organic compounds, organic semiconductors, right? This the P dot PSS is not like a pure semiconductor. This is a conducting layer. BCP, this is also conducting layer which restricts holes, but it can transport the electron from cathode to inside the device. Now come to the emission layer. So this emission layer, here I told that inside the emission layer, electron and hole both can recombine. So this may be, so p-type, whole transport layer, you can also use as a p-type semiconductor as a whole transport layer, and n-type semiconductor as a electron transport layer, because n-type semiconductor that transports electron. Okay, and p-type semiconductor transports hole, right? So but emission layer, that may be p-type or n-type. Okay, it's up to you. Most popular emissive layer is the AlQ3. Okay, but if you want to design suppose blue LED and blue OLED or red OLED, so depending on the band gap of the semiconductor, you have to put the emissive layer inside this electron transport layer and hole transport layer. So many emissive layers are there. Okay, depends on the band gap. If suppose you want to design different band gap with different color OLED, so accordingly you have to choose the band gap and the materials. So molecules, so type of the molecules and type of the band gap, okay, that decides the which color will be emitted from the emission layer. It may be p-type semiconductor and n-type semiconductor, but the band gap should be aligned in such a way. Okay, so no electron will transfer from emission layer to hole transport layer, and no hole will transfer from emission layer to electron transport layer. That's why we have to use the hole transport layer, electron transport layer, which restricts electron from the other side, okay, and from which restricts hole from the other side. This is the basic structure. So next class I will discuss about the energy level diagram and how the energy level diagram is proper aligned to design the organic light emitting diode and types of the different kind of the organic light emitting diodes. Thank you.